This is the second part of resolution of forces. So when we have multiple forces acting on an object, or more than three forces, such that we cannot use our triangle of forces, we need a different method. So instead we can break down the magnitude of forces acting on a plane into their components. So their parallel force, this is in the I direction, or it's parallel to the plane. The perpendicular component of the force refers to the j direction, which is the direction perpendicular to the plane. Note that these forces can be positive or negative. Let's have a look at what I mean. Here is our plane. I'm going to make the right the positive direction, the left the negative direction. The same for our perpendicular axis. This axis is perpendicular to the plane. Going up is positive, going down is negative. So the plane itself, we can imagine being that I, or that unit vector direction, horizontally, and the j direction is the direction that is perpendicular to this plane vertically. If we have a force F, we can break it down to its Fi component, or the component force of F in the I direction parallel to the plane, and the Fj direction, which is the component perpendicular to the plane. We can then form expressions for Fi and F of j. So notice that cos theta would be Fi over our force F, and this gives us a way of finding Fi. So F cos theta is equal to the I component of F, and similarly we can do the same thing to find an expression for Fj. Sine theta is equal to F of its perpendicular component over F itself, and then rearranging that we get F sine theta equals the perpendicular component of F. Let's put this into practice with an example. So our example says determine the parallel and perpendicular components of forces F, G, and H acting on the object below with respect to the plane. So before we do this, let's just look at some information that we have. At your plane is that dotted yellow line that's tilted slightly from the horizontal. The perpendicular direction from the plane, okay, as that is 90 degrees from the plane. We have the positive direction of the plane and the negative direction, the same with the positive perpendicular and negative perpendicular directions. Notice that for force F, I've just put in my Fi component and my Fj component. If I want to find the Fi component, we just use our formula that Fi equals to F cos of theta. F we know was 10 kgWts, and theta is 45 degrees. That's just your angle to the plane from F. Cos of theta is root 2 over 2, so I have F of I is 10 root 2 over 2, or if you simplify, it's 5 root 2 kgWts. This is positive because notice that F of I is going to the positive direction of I, or the positive direction of the plane. For Fj, we do a similar thing, except this time remember that it will be sine theta. Again, sine 45 is root 2 on 2, so we'll actually get the same thing here, that the force in the perpendicular component to the plane is 5 root 2 kgWt. Again, this is positive because this perpendicular component is upwards. We can do the same with G. For G, if we're trying to find the horizontal component along the plane, notice that G actually doesn't go to the left or to the right. It's just straight up along that perpendicular component. So it is 0 in the I direction. So G of I is just 0. G of J, we'll notice that all of our vector G is in that perpendicular direction, positive, and we know that G is 5k WT in this direction, solely in this direction. So GJ is 5. For H, notice that H of I should be negative, right? I'm going down the plane in that negative I direction. Our formula again, notice that the angle between the plane and H is 30 degrees and H itself is 7. So we can say that negative HI, remember the negative direction, will be 7 cos 30 degrees. In other ways, you can put this as HI is equal to minus 7 cos 30, and cos of 30 is root 3 on 2. So by breaking it down into components, you can see that you don't just get a number, but this number can be positive or negative depending on the direction the force is acting. That's a little bit different to when we use triangular forces. HJ, again negative because it's downwards perpendicular to the plane, is equal to minus 7, this time sine of 30, which is sine 30 is a half. So we get minus 7 on 2 kgwt's is the component force of H in the perpendicular direction to the plane. So how does this help us with problems where we have an object at equilibrium on a plane? So if forces are acting on a particle that is in equilibrium, then the sum of all their I component forces is 0. You can also do it the other way and say the sum of all the J component forces is also 0. So if we look at our previous example, we can see that the particle is not at equilibrium because Fi plus Gi plus Hi, 5 root 2 plus 0, minus 7 root 3 on 2 from the answers on the previous slide, that does not equal 0. Fg plus Jg plus Hg also does not equal 0. We have 5 root 2 plus 5 minus 7 on 2. This indicates that this particle is not at equilibrium, so it is not still, or it is not moving at a constant velocity. We're going to see an example where the particle is at equilibrium. Question 2 says an object of mass 20 kg is placed on a smooth plane. So here is my plane and here is my object. Now the plane is inclined at 28 degrees and the mass of the object is 20 kilograms. Put in here, if our force was parallel, it would be along this dotted line. And we know that the angle that this dotted line makes with the horizontal would also be 28 degrees. But our actual force makes an angle of 20 degrees with the plane. So I can put that 20 degrees in right here. This force is a string and it is holding the object in place. So this object is in equilibrium. We also know that we will have a normal force that is perpendicular to our plane. And that's important too. So notice that one of my dotted lines is the line that's parallel to the plane. This is kind of like my I direction. It goes both in the positive and negative direction. We also have our normal to the plane. So remember that is like our J direction, and that corresponds to where my normal force is. It also has a positive and negative direction. So we're going to call the upward part of that J, and then the negative part of that in the negative J or negative perpendicular direction. Using what we saw in the last slide, we're going to find the tension of the string or our force F. Because the particle is at equilibrium, we can use the fact that Fi plus Ni plus Wi will all equal to 0. To find out what each of these are, we can use our formulas. You could also use Fj plus Nj plus Wj equals 0, but I tend to use the I component when we're looking for force F. We know Fi is F cos of 20. We know that Ni, well, that normal force has 0 I direction, so that will just be 0. And for Wi, we need to find the angle that W makes with our parallel line to the plane. So you can see that there'll be a straight line, my I direction here. So if we can find our straight line, then we can say that theta equals 180 degrees minus 28 plus 90 because of this straight line. So 28 plus 90 plus theta should equal 180 degrees because that is all in a straight line along that parallel line to the plane. In this way, we can find that the angle between W and the parallel direction of the plane is 62 degrees. So I'll put that in there. Now I can find Wi. Remember, Wi will be negative. We'll have Wi is equal to negative 20 cos 62. Now you've formed an equation where you can find F quite easily. Just take the minus 20 cos 62 to the other side. Just take the minus 20 cos 62 to the other side. F equals 20 cos 62 over cos 20, which is approximately 9.9 kgW. Lastly, we need to find the normal force here and the magnitude of this force. So because this object is in equilibrium, we also know the sum of the j components will equal 0. We're going to use this to find the normal force in this question. And I tend to use the sum of the j components for the normal force because the normal force is in that perpendicular direction to the plane. We know f of j is just f sine of 20. We know that n of j, well, notice, like we said, that normal force is only in the j direction. So n of j is just the whole of n. Wj, well, that will be negative because we're going downwards. And we know that it equals to minus sine 62 degrees. So all of this equals 0. Now we can fill in for f because we found that in our previous part of the question. In exact form, we know that f was 20 cos 62 over cos 20. And we know what W was as well. W is just the weight, which is 20. We know W is the weight, which was just 20. If I sub all of this into the equation, this is what we get. Now all we have to do is solve for n. So take everything else to the right-hand side, and we'll get something a bit strange. But when we simplify it, we get that the strength of n is approximately 14.42 kilogram WTs. So that is how we do resolution of forces on a plane into two components. They're parallel and